Okay, so in the textbook, it talks about this branch of chemical reactions, redox versus non-redox reactions. And the first part of the chapter talks about redox reactions. And like I said in the video, a redox reaction is a reaction that involves a transfer of electrons from one element to another element. And we said that a reduction occurs when an atom gains an electron or more than one electron in a chemical reaction. And an oxidation is when an atom loses an electron. And so the way I remember this is Leo the lion goes grr. So loss or losing electrons is oxidized, gaining electrons is reduced. So if you can remember that, that'll actually be helpful for your biology classes too, because it may come up in biology. And then assigning oxidation numbers is pretty important. We're going to be doing this during our review today, but I just wanted to quickly brush up on it. And it says that anytime you have an element in its pure form, the oxidation number is going to be 0. So like with aluminum metal, be 0. With O2, it's still elemental. That's elemental oxygen, even though there's 2 atoms in O2. It would still be 0 for each atom. And then number 2 says treat all other atoms as if they were ions, even if they're not ions. Just pretend like they are ions. So with sodium and chlorine, we've got +1 and -1. For H2O, even though it's a covalent molecule, we treat hydrogen as an ion and have it be H+, and then oxygen would be 2-. So we can kind of break things down that way. All right. And then the last one is that neutral molecules should have a sum of oxidation numbers that adds up to 0. And then polyatomic ions should have a sum of oxidation numbers that adds up to equal their charge. So we can kind of keep track of things that way. But in some cases, kind of like I did in this example with MnO4-, we had to infer the charge of the manganese, right? And the reason we had to do that is if you look at the periodic table, that entire central group, we can't really easily predict the ionic charge. But when we go up and look at oxygen, oxygen is over in 6A, and so we knew it would be 2-, so we could kind of do some simple math to figure out the charge of the manganese that way. Does this make sense so far?
Yeah.
Okay, perfect. So now let's jump into the next part. And this was a video that was actually misplaced. So when I send out a video tonight, I'll kind of point out this video in case any of you missed it. It was misplaced in the video list. But this talks about oxidizing agents and reducing agents. And it says that an oxidizing agent is a reactant that oxidizes another reactant. But it's interesting, an oxidizing agent gains electrons from whatever is being oxidized in that process. Therefore, it actually gets reduced. So it's confusing. But we'll practice this a little bit when we do some of these problems. And then reducing agents are the opposite. A reducing agent is something that reduces something else, but gets oxidized in the process. And then I put a note here that an oxidizing or reducing agent is an entire reactant, not just a single atom. And then I walked through a few problems here. How many of you watched this video? Did any of you?
I did.
A couple people?
I did.
Okay, we'll do some more practice problems like this though, because what I've found is students tend to struggle with problems like this because it does look really scary. So let's go ahead and just work through some practice here. So here's the first one I'm going to do. And we're going to have strontium, that's element Sr. We're going to combine this with oxygen. And in this reaction, we're going to make strontium oxide. What's the first thing I should do? Does anybody spot a problem even before we do redox chemistry?
There's 2 oxygen on one side.
Yeah, there's 2 oxygens on the left side, but only 1 on the right side. So what I would do is first try to balance this reaction before I do anything else. So like you said, there's 2 oxygens on the left over here, but only 1 here. So I'm just going to multiply this side by 2. So now I've got 2 oxygens on both sides. That looks good to me. And then I would check for the strontium atoms. Well, I've got 2 over here. So I would need to multiply this side by 2. So now it looks like I've added reaction coefficients in a way that allows me to have the same number of atoms on the reactant side as the product side. It's really important to do that before you do much else with chemical reactions. Okay, so now what I want to do is assign oxidation numbers. So let's think about SR right here, the strontium. What would the oxidation number be for this reactant or element?
+2.
+2.
Yeah, it's tricky though, right? If you assume that it's an ion, I would agree with you. But is it in its elemental form?
Oh, yeah.
Yeah, exactly. This is what throws people off, is that when an element's by itself, this is elemental, which means that its oxidation number is going to be equal to 0. All right? Okay, so let's do the same thing with oxygen now. We've got O2. What would the oxidation number be for O2?
2 minus.
Again, it's one of those things that's tricky, right? If we assume that it's an ion, I would agree that it's 2 minus, but it's elemental, it's by itself. So I'd say this, because it's in its elemental form, its oxidation number is going to be equal to 0, right? And that's a really common mistake that students make, is they immediately jump to the ion, but you need to first check if it's by itself, because if it's by itself, it's just 0. Okay, now let's go to the other side, the product side. So we've got strontium over here, but if you notice, the strontium is no longer by itself. It's bonded to the oxygen. So what would the oxidation number be now?
So that's where the +2 would come in.
Exactly. So now this would be +2. Okay. And now let's take a look at oxygen. What would the oxidation number be now?
It'd be the -2.
-2. Perfect. Okay. So now let's go ahead and think about it this way. Let's focus on the strontium now. So we're going from the starting material side to the product side. And over here it said we went from 0 to +2. Does that mean we gained or lost electrons?
Lost.
Lost electrons. Okay. So we could say that each SR lost 2 electrons, right? Because we went from 0 to +2, that implies that each of them must have lost 2 electrons. Okay. So what occurred with this atom? Was it oxidized or reduced if we lost 2 electrons?
Oxidized.
Oxidized. So I'd write SR was oxidized. Perfect. Okay, now let's go ahead and do the same thing for oxygen up here. And I'm going to slide everything down. Okay, so for oxygen, we started out with an oxidation number of 0, and we went to 2. So did we gain or lose electrons?
Gained.
Yeah, we must have gained 2 electrons. So each oxygen gained 2 electrons. Okay, and we know if we gain electrons that it must be a reduction, right? From Leo goes Gur. So oxygen was reduced. Okay, so now the tricky part. Let's assign oxidizing agents and reducing agents. So let's think about this element over here. So if we think about it, right, the strontium we said was oxidized. But what does that tell us about the reagent itself? Was it an oxidizing agent or reducing agent?
Reducing agent?
Yeah, exactly. One way to always remember it is it's kind of flip-flopped. So this right here is going to be our reducing agent. Oop. And then this reagent over here, O2, this must be our oxidizing agent, because it has the atom or element that's getting reduced in the overall process. Make sense? And oftentimes when I do these, I create a lot of space, almost exactly like what I'm doing now, just to kind of mind map what's going on. And it can make it a little easier. But often if you just look at an equation and it's asking you multiple choice questions like what's oxidized, your brain just goes on like overload mode and you don't know where to begin. But if you spread out on paper, all of a sudden you can map it and flow arrows like this and make it a little easier on yourself. Let's try another one.
So really quick,
Yeah.
with the problem, I'm having something that's kind of conflicting in my brain, and I know we're going to eventually get to it. But so with the +2 over on the right, since there's 2 of them, why don't we do it that there's 2 +2s? I know that's in a different section, but can you remind me what that is?
Yeah, so let's think about the reaction a little bit differently, right? So I'm just going to draw it over here. Just a thick line. Really what this is saying is on the starting material side, we've got 2 of these atoms. And then we've got an O2, which if you do the Lewis structure, O2 actually has a double bond like that. We could just write O2, it doesn't matter. So we've got 2 strontium atoms reacting with an O2. And then we're creating 2 of the strontium oxides, right? So let's think about it this way. Over here on this side, we said that each strontium atom lost 2 electrons, right? So how many electrons were lost total? I'd say 4, right? Because we have 2 atoms and each of them lost 2 electrons. So 2 SRs lost 2 electrons, which equals 4 electrons. Okay. And then over here, oxygen, we said each oxygen. So 2 oxygens gained 2 electrons, again adding up to 4 electrons. So that's another unique thing that we don't get into a lot in Chem 121, but we also need to bounce our electrons during these redox reactions. But as long as you follow the basic guidelines that I'm presenting right now, I'm not going to try to throw a curveball at you. And you don't need to bounce electrons beyond just bouncing the reaction itself.
And so that's where the difference comes in, is it's the electrons, not the charges.
Yes, exactly.
Okay, thank you. Yeah, I knew there was something that I was confusing, and that was it. Thank you.
Yep, no problem. Great questions, everybody. Let me just erase this and then we'll do another one. And how many people here are going on to 131? I was going to ask that. Chem 131. Is anybody?
There's a possibility that I might end up doing it.
Okay, well, I'll do a reaction for 131 just to help too. But let's do another practice one here. Let me go through my list. I want to find a more interesting one. Yeah, let's do this one. This is a good one. So iron can react with oxygen, O2. And when they react together, you essentially get rust. So you can think about steel rusting in an oxygen environment. It's the iron and steel doing the rusting. And you form iron and oxygen in a compound where it's a 2-to-3 ratio. Okay, so what do we do first? We've got to bounce it, right? So when I look at this, I'd immediately start with the iron and I'd say, well, we've got 2 irons on the right, but only 1 on the left. So I'm just going to go ahead and throw a 2 in front of the iron here. That way I have 2 irons on each side, right? Okay. And then I would go over here and I'd say, well, over here, I've got 2 oxygens here and 3 over here. And this is a point where a lot of students kind of get panicky and they're like, well, they're not balanced. And it's not intuitive how to fix this. But does anybody have an idea on what we should do?
We should put 2 for the one on the right, and then adjust the left again.
Yep. Yeah, if you want, one thing you can do is you see how we've got a 2 here and a 3 here. If we cross multiply, we're going to even out, right? So what I would do is in the next step, like I said, if there's a 3 down here, I'll just slap a 3 in front of the other molecule. And if there's a 2 down here, I'll just slap a 2 in front of the other one. Because that way, we're going to have 6 oxygens on each side now. Am I done?
No.
No. What else do we need to fix now?
We need to change the iron.
We need to change the iron, right? So we've got 4 irons on the right, which means we need to change this to a 4. And students will often ask me, isn't there a more elegant way to do this? And the answer is not really. Oftentimes you just have to do a lot of guessing and checking, but always double check your work at the end to make sure that things bounce out. Okay, so now we've got it set up. Okay, so let's do iron over here. What's the oxidation number going to be?
0.
It's going to be 0. Why is it going to be 0?
Because it's in its elemental form.
Yep, it's elemental. So I'll just make a note here. Okay, and oxygen over here, its oxidation number would also be 0, right? Because it's by itself, it's elemental oxygen. Okay, and now let's jump over to the other side. And let's do oxygen right here. So now oxygen's involved in a compound, right? It's in something new. So what would the oxidation number be?
-2.
-2, right? Because oxygen as an ion would want to be -2. Okay, so now we can go ahead and focus on this part because we've got it done. And it looks to me like we're going from 0 to -2. Does that mean we're gaining or losing electrons?
Gaining.
Yeah, I'd say gaining 2 electrons. So I'd say each oxygen is gaining 2 electrons. Does that mean it's being oxidized or reduced?
Reduced.
Reduced, right? Leo goes Gerd, gaining electrons is reduction. So oxygen is reduced. Okay, now the tricky part. This iron here, what's the charge for iron? Or do we know as an ion?
We don't know until it's balanced.
Yeah, we don't
that's
know
how we
in this
figure it.
case because iron is a transition metal. And we said that transition metals don't have a predefined charge. We actually have to infer it. But that's okay. Let's kind of think about this abstractly. And so what I'm going to do is I'm just going to draw this out symbolically. We know that this compound is made up of 2 iron atoms with some sort of charge. So I'm just going to put question marks for the charge. And then we know we've got 3 oxygen atoms. So I'm just going to draw 3 oxygen atoms. And we're going to treat these as 2 negative, right? Because we're treating them as ions. Make sense so far? Okay, so from this pictorial diagram that I have right here, we should be able to kind of infer what this charge should be. What charge should that be? In order for things to be completely balanced.
+3.
+3, right? Because if we think about it over here, we've got 2, 2, 2, that adds up to 6 negative, which means that this side must add up to be 6 positive to balance everything out. Okay.
Does it usually work out like to do kind of like how we were like the 3 kind of goes to cross multiply? Is that like a faster way or does that not work?
You can do it that way if you want. I just like doing it this way because some people are very visual and they
yeah.
Yeah. So
I
whatever
like
works for you.
No. I just wanted to make sure it would work.
Yeah. So this way we've ensured that our positives and our negatives canceled, and we were able to infer that the charge for each iron atom must be +3, which means that the oxidation number must also be +3, right? Okay, so now we can go through and we could say, well, each iron, did it gain or lose 3 electrons if it went from 0 to +3?
Lose.
Yeah, so each iron lost 3 electrons. And if we're losing electrons, that means that iron was oxidized. Perfect. So it's kind of neat, right? If we think about the irons, right? Over here, I said that each iron lost 3 electrons, and we've got 4 iron atoms. So how many electrons were being transferred?
6.
Not quite. We had 4 iron atoms, each of which lost 3 electrons. So I'd say 12 electrons overall were being transferred in this reaction. So we do need to account for the bouncing too, to say, okay, overall, we must have moved 12 electrons. And then if we go to oxygen, we can even double check that up here. And we could say, well, over here, each of the oxygen atoms in O2 gain 2 electrons. So if we have 2 oxygens in O2, that means there's a total of 6 oxygens and 3 O2s, right? And if we've got 6 total oxygens gaining 2 electrons, that means that there's 12 total electrons being moved. So again, you can kind of see this bouncing effect where we're transferring electrons from one element to another, which is pretty neat. Okay, now let's do the last part. This reagent, the iron, was it acting as the oxidizing agent or the reducing agent?
Reducing.
Reducing agent, right? Because it got oxidized in the process, it must be flip-flopped. And we'd say that this is going to be the reducing agent. And then over here, this must be opposite, right? Because it contains the atom that was reduced, we can say that this must be the oxidizing agent. So perfect. Is this making more sense? How many of you want to do another one like this?
I don't think it would hurt.
Don't think it would hurt? All right, let's do one more kind of like this, and then I'll do an organic chemistry one, and then we'll kind of twist it around a little. Okay. Let me go through my list of potential ones. Oh, here's a fun one. Actually, sorry, I'm changing my mind. Let's do this one. So we've got Cl2, this is chlorine gas, and sodium bromide reacting together to make sodium chloride plus elemental bromine. Okay, so first things first, we've got to ensure that everything is balanced. So if I look at chlorine over here, I've got 2 of them on this side, on the left, but only 1 on the right. So I would go ahead and throw a 2 in front of here. That way I have 2 chlorines on each side. Then I would jump to my sodium. I'd say, well, over here, I've got 1 sodium, but now I've got 2 sodiums on the right-hand side. But that's okay, I'm just gonna multiply this by 2. That way I have 2 sodiums on both sides. And then I would go to bromine and I'd say, well, now over here, I've got 2 bromines and I've got 2 bromines. So it looks to me like everything's canceled, but it's always a good idea to check at the very end just to ensure that you haven't made a simple mistake. Okay, so now let's go ahead and do this one. So this one, we've got Cl2. What would the oxidation number be?
0.
0 because it's by itself, right? It's not a compound. Okay. And then let's go ahead over here and do sodium. What would the oxidation number be for sodium?
+1.
+1, yeah. Because it's in a compound, we'd treat it as an ion. Okay, now let's do bromine. We actually have a third element here. What would the oxidation number be?
-1.
1 minus.
Yeah, -1. It's in that 7A column, which is always going to be 1 minus or -1. Okay, now let's go ahead to the other side. What would the oxidation number be for this sodium?
+1.
+1. Again, it's in a compound, so we treat it the same. And let's go ahead and do chlorine right here. I'll just toss this underneath. What would the oxidation number be for chlorine right here?
-1.
Okay, -1 because now it's in a compound. It's not elemental anymore, right? So we'd want to treat it as an ion. Okay, and then bromine over here, Br2, what would the oxidation number be?
0.
0, exactly, because it's elemental now. It's not in a compound bonded to different types of atoms. Okay, so now let's kind of do one atom at a time. So I'm going to start with chlorine, follow it from my starting material side to my product side. So it looks to me like we went from 0 to negative. We must have gained an electron, right? Because it's getting more negative. So I'd write that each Cl gained 1 electron. Okay. And if we're gaining electrons, what does that mean? Were we oxidizing it or reducing it?
Reducing.
Reducing, right? Because it gained electrons. So it's in the GR, gains electrons is reduction. So chlorine was reduced. Okay, now let's do the weird one. So sodium went from +1 to +1. Was this oxidized or reduced?
It was neutral.
Yeah, it's a trick question, right? If no electrons were moved around, it's not a redox. So no reduction or oxidation occurred. So we don't even need to keep track of this if we really don't want to, because we know no electrons are getting moved around in this process, and that's fine. In a redox reaction, you may have spectator atoms where no electrons really are doing anything. In fact, I'm just going to erase that now just to keep things from getting super cluttered. Okay, and now let's do our last one. Got bromine going from -1 to 0. So did it gain or lose electrons?
It lost.
Yeah, it must have lost electrons because it's getting more towards that positive territory. So each bromine lost 1 electron, which means that bromine was oxidized. And this kind of brings me to my next point, is oftentimes when people hear about, something being oxidized, they immediately in their head think, well, that sounds like oxygen, right? Oxidized oxygen, oxidized oxygen. But a redox reaction doesn't always have to involve oxygen. This is a good example of a redox reaction where oxygen wasn't involved at all. So keep that in mind when you're doing these sorts of reactions, that you don't have to have oxygen for a redox reaction to occur. Okay, so now the last part. Chlorine over here on the left, was this our oxidizing agent or our reducing agent?
Oxidizing.
Oxidizing, because we could say it was reduced. It contains the element that was reduced. So this must have been our oxidizing agent. Let's do this one down here. This one contains the group that was oxidized, which means the whole thing must have been the reducing agent. Make sense? Awesome. And a lot of times students will watch this and they'll say, okay, this is great, but how is this related to nursing? How is this related to any allied health career? And the way I like to describe it to like non-scientists is that our body basically runs by moving electrons around, right? When you think about digesting food, metabolism, things like that, it's all redox chemistry. It's fascinating when you think about it, but the movement of electrons in our mitochondria is vital to everything we do. It's what gives our bodies energy. So it does seem kind of abstract when we draw it out like this, but it's essential towards biochemistry. So let's take a look at something a little bit different. This next one, we've got CH4. This is methane. It's primarily what makes up natural gas. So if you have a gas furnace at home, this is what's heating your home. And with a methane furnace, you have to pull oxygen out of the air and you burn it, right? In a furnace. Does anybody know what the byproducts would be when you burn methane?
CO2.
CO2. So this is one thing that's been talked about a lot in the news, is trying to reduce CO2 emissions. Methane's arguably one of the greener fuels in terms of amount of CO2 produced, but it's still a greenhouse gas. What's the other product? Does anybody know?
Water.
Water. Yeah, a lot of people, when they think of their furnace, they don't think of water, but the reality is you do produce a fair amount of water. It's just being kicked out as water vapor. Okay, so we're not quite done yet. When I look at carbon, carbon looks balanced. When I look at hydrogen over here, I've got 4 hydrogens. Then over here, I only have 2. So I'm going to go ahead and throw a 2 on this side. That way I've got 4 hydrogens on both sides. Okay, so I'm almost there. Now I go over here, I've got 2 oxygens. And some people would immediately hop over here and say, well, I've got 2 oxygens, I'm done. But am I done?
No.
No. You have to count all of the oxygens, right? So I've got 2 oxygens here, and I've got 2 oxygens here, which means I've got 4 total oxygens on the product side. So we weren't done. So to fix that, I would put a 2 in front of the O2 here, and now it's balanced. So make sure you don't rush too fast, because it's a pretty common mistake for students to make when they're just trying to work through a problem. Okay, so now the tricky part. Let's draw the Lewis structure for CH4. So I'm going to completely divide this. So carbon, we know, has 4 valence electrons. So I'll do 4 valence electrons for carbon like this. All right, and it says we have 4 hydrogens. How many valence electrons for hydrogen? Just 1, right? So I'll stagger these around. We know that electrons want to be paired. So what I would say is, well, let's pair these up like this. And that looks fine to me, right? We've created our CH4 molecule. And then down here, we've got oxygen, which is O2. And we've got 2 of them. They have 6 valence electrons, so I'll show it like this. And we can pair up this unpaired pair of electrons, but am I done?
No.
No, we want to pair up this one too. So really, if we redraw these and make them look prettier, I could redraw CH4 with bonds between all of those, right? And I'm going to do the same thing for oxygen. And we know we've got 2 of them, so I'm just going to draw this out twice. And next is CO2. And CO2 is one of the molecules we did in our molecular modeling lab. And if you remember, it looks like this. And then last but not least, we've got H2O, which was also part of your molecular modeling lab. So I'm just going to cheat and copy this over. And draw it out like this. Okay. And I'll show you why I'm drawing this out in a second. But let's go ahead and think about hydrogen. In this case, let's skip carbon for now. What would the charge be for the hydrogen? Or the oxidation number, excuse me.
+1.
Okay, so oxidation number is going to be 1+. And then over here, what would the oxidation number be for the oxygen?
0.
0. Okay, now let's skip carbon. We'll come back to carbon at the end. What would the oxidation number be for the oxygen and CO2 now?
-1 or -2.
-2, right? Because it's in group 6A. So if it were ionic, we would treat it as -2. Okay. And then over here, we've got hydrogen. And it's in a compound. So what would it be?
+1.
+1. Okay. And let's think about it this way. The oxygen over here, what would this be?
-2.
-2. Okay. So we skipped carbon, but let's kind of take a look at what we have done. So let's think about hydrogen here and here. Is this doing a redox reaction? Doesn't look like it, right? Because it was +1, +1. Okay. So that's fine. But let's take a look at oxygen now. So oxygen actually, in this case, is going to 2 different molecules, right? But you see how in either case, it's going from 0 to -2. So over here on the starting material, whoop, that's not what I wanted to do. Over here on the starting material side, it's 0. But either oxygen on the product side, whether or not we go here or here, it's going to -2. Okay, so is oxygen gaining or losing electrons?
Gaining.
Okay, so each oxygen is gaining 2 electrons, which means that oxygen is reduced. Okay, so now the tricky part, carbon. If you remember on the table that I gave you where it showed predictable charges for elements, carbon wasn't actually listed. So group 4A is pretty unpredictable, just like if we were dealing with a transition element. It's just hard to predict the oxidation number of carbon. But let's think about it this way. Okay. If we had 4 hydrogens that were +1, what does that tell us about the carbon? What oxidation number must it be?
-4.
Yep. In this case, it must be -4, kind of like we were doing with that ionic compound before. Do you remember when we were doing that? Where we had to infer the iron charge based on the oxygens? It's basically saying that this net total is going to be +4, which means that this net total to be neutral must be -4. So we had to infer that from oxygen, or sorry, from hydrogen. Okay, now let's do the same thing over here.
So just, sorry, I was like a little bit behind. So with the, because I thought before you said it was a ON number of -1, but I didn't understand how you were getting -1 if they're equal, I guess.
Are you talking about the hydrogen atoms?
You know what, I was just a little confused earlier when I saw the -1 earlier, it was erased, but I was just wondering if, was that just talking about the hydrogens? I guess I was a little lost.
Oh, sorry. So over here, we said that hydrogen originally if we think about the oxidation number for it as a compound, what would the oxidation number be?
Oh, -1.
Positive one.
Positive 1, sorry.
Yeah, so for this one, it must be oxidation number of +1. However, we've got 4 atoms, which means that the total is +4, right?
Mhm.
And then from that, we can say, well, if that's the case, then the oxidation number of carbon must be -4 to cancel out and be neutral, right?
Yeah.
So we have to make some kind of simple math decisions from there. Does that make more sense?
Yeah, that makes, I guess but what, before, did you guys have a -1 here, or was the oxidation number of the total ion, or was it, it's just neutral, right? Or is it, am I missing something?
Yeah, did I accidentally write oxidation
No,
number of -1?
I don't know. I think I got confused. So that makes sense. That I can.
Okay. Yeah, sorry if I had a typo. Sometimes
No.
writing and talking, I make mistakes.
No. I just probably read it wrong. So that makes sense.
All right, so let's go to the next one now. And I'm just going to erase this to keep things kind of neat and tidy at this point. But now let's think about CO2, right? We've got to figure out the oxidation number of carbon. So how are we going to do this?
We use the oxidation number of the oxygen that's connected to it.
Yeah, exactly. So if we think about these oxygens right here. So those oxygens each had an oxidation number of -2, right? That's what we set up above. So the total oxidation number for all oxygens is -4, right? Because we've got 2 oxygens, each with a -2.
Right.
Make sense? Okay, so now we can go to the carbon and we can say, all right, what's the oxidation number for carbon? What must it be?
+4.
+4 in order to cancel out the -4. Perfect. Okay, so now we can look at this and we can say, all right, in this process, did we gain or lose electrons?
We lost electrons.
Yeah, we lost how many electrons?
8.
Exactly. So each carbon lost 8 electrons. That's a huge transfer of electrons. So in this case, carbon is oxidized. All right, so now let's go back to the beginning. CH4, was this our oxidizing agent or reducing agent?
Reducing.
Okay, because it contains the carbon atom, it contained an element that was oxidized. This must be our reducing agent. And then down here, because the oxygen was reduced, we can infer that this is going to be our oxidizing agent.
And in this particular case, is that because we are coming out with ions from adding ions to elements?
Sorry, say that again.
So on the left-hand side, you have the compound and the element of oxygen, and you're adding those together to get the CO2 in the water. Are we getting the reducing and the oxidizing agent on the left-hand side? Because I guess I don't know what my question is.
No, it's okay. Yeah, the way I normally tell students to remember this is your reducing agent, this thing right here, always contains the element that is oxidized and vice versa. So if you can remember that, you'll be in good shape.
Right, yeah, okay.
Yep. And sometimes, like I said, it's easy to draw these out, but I like doing this as review. It is confusing when you're dealing with covalent compounds to treat things as ionic. But the way I like to think of this is that the more electronegative atom is going to win all the electrons. if you are interested in kind of seeing other organic compounds worked out, I can show you some other organic compounds. But I think this system that we went through right here is a pretty good rule of thumb, is just try to make those inferences if you don't know the oxidation number of a particular element.
Okay.
Make sense?
Yeah.
Awesome. Do you want to do any more, or are you kind of feeling redoxed out right now?
I think I'm starting to get it. I think I'm going to leave that one up to everybody else. Everybody else is kind of quiet.
I wouldn't mind another one.
Another one? Okay. How about this? We'll do one more, and then we'll kind of leave things open just for general question and answers related to redox or not. Okay, so let's do this one. Trying to find a fun one. Trying to remember, let me see if we did this one already. I can't remember which ones I did in my example video. Okay, let's do this one. So in that Brainiacs video I gave you in one of the early weeks, they showed the alkali metals being dumped into a bathtub. Do you remember that?
Yeah.
So one of them is sodium. And sodium you can combine with water. And when you do that, you make sodium hydroxide plus hydrogen gas. Why do you think the reaction, oh no. Okay, sorry, I was freezing. So why do you think this reaction exploded before we go and do anything else? I'll give you a hint. If you are familiar with history, how many of you have heard about the Hindenburg?
With the hydrogen?
Yeah, it was filled with hydrogen gas. It was like a blimp filled with hydrogen and it exploded, right? So in this reaction, you make a bunch of hydrogen gas where if it's hot enough, it'll actually explode. So that's why in that video, they were showing explosions, is they were rapidly producing hydrogen gas that could actually explode. So this is kind of a neat reaction, but we need to make sure it's balanced. So I'd say we've got one sodium. Looks good to me. Then I would go to my hydrogens. Got two hydrogens right here. And then over here, I've got one hydrogen and I've got two hydrogens. All right, so now it gets a little bit tricky. What do you think we should do?
Double the most complicated one.
Yeah, what I would maybe do is double the most complicated compound is a good rule of thumb. So in this case, I would say let's double this one, right? Because if we do that, now all of a sudden we've got 2 plus 2, which is 4 hydrogens. And that's a lot easier to fix on the other side, right? Because now we can plug in a 2 here and we could have 4 on this side and 4 on the other side. Make sense? Okay, and now let's go to oxygen. It looks like we've got 2 oxygens on the left side here and 2 on this side here. So looks like we're almost done, but what else do I need to fix?
Na?
Yeah, the sodium. It's important to go back and counter what we changed when we multiplied this by 2, which also changed the number of sodium. So now we're on track. Okay, so sodium. What's the oxidation number going to be for this sodium?
+1?
Not quite, it's by itself.
Oh, 0. Yeah.
Yeah, so it's going to be 0. Okay, now let's do hydrogen. Oxidation number. It's in a compound.
+1?
+1, perfect. Okay, and then let's do oxygen. Oxidation number for oxygen in a compound.
-2?
-2, perfect. Now we'll go over to sodium again. Oxidation number must be what?
Now +1.
Now +1, exactly, because it's in a compound now. And then we can jump over to oxygen here. Oops, sorry, that should be purple. Oxidation number for oxygen here.
-2.
-2.
Okay. With the ones that you kind of had us memorize, like that would be hydroxide. Would you like when you're doing reactions like this, you just like break them up into individuals, or do you keep them together?
Oh, that's a good question. So let's think about this separately, right? So I'm just going to kind of make a note down here and say, okay, so sodium hydroxide is Na+1, and then we've got OH. And what's the charge for this? Do you remember?
I thought it was -1.
Yeah, exactly. So we could look at this and we could say that the charge of this is 1-, right? Additionally, what we could say is, well, we know that hydrogen in this case must be +1. And then oxygen, like you said, if we treat it as an ion, must be -2. But you see how these two numbers add up to equal the -1?
Yeah.
So it's kind of a neat feature of these polyatomic ions too.
Okay, cool.
Yep. Okay. So we've got through oxygen. Now let's jump into the hydrogen here, which I guess we already kind of hit. So this oxidation number must be what? For this hydrogen. +1, right? But here's where it gets a little confusing. What would the oxidation numbers be for these hydrogens?
0.
0, because they're by themselves. Okay, so now we've done all of our bookkeeping, right? Let's assess what's going on. So let's go back to sodium. So sodium went from 0 to +1. Did it gain or lose electrons?
Lost.
Yeah, so each sodium lost 1 electron, which means that sodium was oxidized. Okay, now let's go to oxygen just for fun. So oxygen went from -2 to -2. So what did we learn about it?
It gained 4.
So -2 to -2 looks like there was no change, right? So when I look at this, I'd say oxygen wasn't participating in redox chemistry. Electrons weren't being transferred in this process here, at least not for oxygen. In fact, I'm just going to erase this and just say oxygen was kind of a bystander during this process. Okay, and now the weird thing, hydrogen in this case, one could argue that some of the hydrogen didn't experience redox chemistry, right? It went from +1 to +1. But let's think about the other hydrogens. This one went from +1 to 0. So then we could say that each hydrogen must have gained 1 electron, which means that hydrogen, some at least, was reduced. Make sense? Okay. And then last but not least, we could look at the sodium and we could say, well, was sodium acting as an oxidizing agent or a reducing agent?
Reducing.
Yep. It's acting as a reducing agent because it contains the thing that was oxidized. And then over here, we could say, well, what was water doing then? Well, water contains the thing that was being reduced. So therefore, it must be the oxidizing agent. Make sense? And I know when I was reading the book goes through this stuff pretty quickly. But where I feel like things start to really click is just doing more practice on your own. So if you can, try to go through the end of the chapter problems that correspond to these sections and work through some of those on your own. And if you ever get stuck, post in the discussion board or email me or message a friend. But practice is how you get good.
Okay.
Any other questions? No, or is everybody just tired? All right, another thing, I was going to make an announcement in the video or in the email tonight, but for the discussion boards, a few people commented on the survey that they felt that the discussion board for the last exam was just way too long. So what I think I'm going to do is split them into chapters. So you can post questions on a specific chapter, but I'm not going to require everybody to comment on every chapter. I'll just say you need to comment on at least one of the chapters before the next exam. Does that make sense? That way, people don't get overwhelmed scrolling through a discussion board that's a mile long. I know it can feel a bit overwhelming at that point. Any other questions?
Sounds good.
Awesome. All right. Well, I might wrap this up here, but if you have any questions while you're studying later today, feel free to email me.
Thank you.
Thank
All right.
you.
Talk to you later.
Thanks.
Thank
Bye.
you so much.